Okay, Hugh, are you ready? 9 o'clock. Let's start.
Yeah. Okay.
Okay. Do something. And okay. Good morning, America, and good morning, good afternoon, European colleagues, and good evening to our Asian colleagues. I see many colleagues from East Asia and South Asia also. So, so welcome you again to this World River and Delta System Source to Sink webinar series. And today is 2021, the number 16. And so we invite Professor Hugh Sinclair from University of Edinburgh come here talk about the mountain process, the sediment routing in the Himalaya-Ganga system. And before I introduce Hugh, I will also mention the International Conference on World Large River will be held earlier August in Moscow, Russia. So this is a hybrid. It's a combination of physical face-to-face and virtual. So is we need some face-to-face interaction, and I'm looking forward to it. Actually, tomorrow I go to Duke University get my Pfizer vaccine. So I'm ready to go. I mean, if everything okay, hope I will meet some of you. So there's 5 topics, as you can see, all the way hydrology, sediment transport, ecosystem, and even the Russia Arctic River system. That should be very interesting. And you just go to their website. And so I'm not any member of organization, I'm just interesting. So I think many of you may be interested in this information. Okay, also this coming Friday, and Carol from Louisiana State University, she will also talk about the Ganges-Brahmaputra system, the elevation change, the sediment dynamic, and even all the way to the canyon system. So really a source to sink study. And it's very nice, you know, Hugh today also talk about, as mentioned, the Himalaya-Ganga system, and same as Carol, as we discussed before we started this session, we have a Stigu Brad, we have a Michael, we have, you know, a couple people already talk about Ganges. This is a wonderful system. Now with these 5 or 6 talk together, I think we can provide a much better understanding, a full picture of this large river system. And hopefully we also can talk about the carbon discharge from this river all the way to the deep sea. And so here is the chair of surface geodynamics in the School of Geoscience, University of Edinburgh. And so this is you know, he graduated from University College Wales and PhD Oxford University, and have you know, a research fellow France, and also lecture in the Birmingham, and visiting school at Penn State, and also coming here to Colorado border. And so so are you visiting a Swiss group?
Yeah, for Boulder, that was really, just so many good people there. I just enjoyed my time. There was Craig Tucker and others. Tremendous place.
Yeah, as you can see, you know, he's interesting. His study expertise in the sediment transport supply mountain belt and the surrounding area. And that's exactly the source to sink topic. We want to understand the source, the basin, and also there are other group people understand after they deliver to the ocean. Like I'm a marine sedimentologist, but I'm also interested in how much coming down the flux part, and particularly involved the tectonic geomorphology and mountain range. So that's great. And so. Okay, Hugh, now I'll give the floor to you, and looking forward to your talk. Now you can share your screen and put a presentation mode.
Great. Okay, and let's get that little pointer. There we are. Good. Is that all nice and clear there, Paul?
Yes, good.
Tremendous. Okay, well, look, thanks very much, Paul, for this opportunity. I think this whole session that you facilitated has been tremendous. And it's also wonderful that it's so international. We've got colleagues who I'm saying good morning to over in the West, and colleagues that I'm saying good afternoon, evening to in the East. So it's really incredible. So this presentation, what I'm trying to do is overview a series of studies that we've been doing over the last decade or so with colleagues here in Edinburgh that I've listed at the top there, but particularly a group of PhD students, some of whom have moved on, Thomas Bernal, Lizzie Dingle, Boris Gaetan, and other current PhD students who are with us now. And then colleagues in India, Vimal, I'm pleased to see that he's here, Rajiv Sinha, and then in Nepal as well, colleagues like Dharam and Basanto Adhikari. So this is very much a presentation of a whole group of people's work with certain emphasis on certain people particularly. So my interests have really come from understanding the way in which topography grows and the relationship. It started with the relationship with flexure, working with Philip Allen and Tony Watts in Oxford. And since then, I've always been fascinated by the way in which mountain belt processes determine the way in which sediment's generated, the way in which it's processed and fractionated as it gets down to the fallen basin, and then within the fallen basin, some of the processes that are occurring within that. So the intrinsic processes, perhaps more than the external forcing, is what I think there has been a lot of focus on over the last couple of decades. So, and of course, there's no necessity to justify why you might want to go and work in this part of the world. I mean, societally, it is probably one of the most vulnerable parts of the planet in terms of population density. Approximately 10% of the global population inhabits and is dependent upon these river systems. And so it's no surprise that the World Bank and others are investing huge amounts of money concerned with how irrigation, how damming, and how climate change are going to affect sediment fluxes and water supplies throughout this region. So very good reasons to try and understand better the rates of sediment production and what controls their dispersal and their distribution. So there we go. So some basic, I'm using this cartoon intermittently just to sort of highlight the source to sink story that we're dealing with, and some basic facts. Some really good work that's come out in recent years from Martin Lupker and now from the Nancy team enable us to make some broad statements about the Himalayan Gangetic system. 95%, one point to emphasize, 95% of the sediment flux coming out of the mountains occurs during the monsoon. So very monsoon dominated. And to put it simply, the erosion rate that the sediment flux and the cosmogenic nuclide concentrations tell us, the detrital data downstream in the plains tells us that the mountains on average have been eroding at about 1 millimeter a year, so a kilometer a million years. And that overall only about 10% of that gets trapped in the fallen basins, and 90% of it gets out to the coastal region and to the delta and out into the Bengal fan. So there's a small amount trapped, and bulk of what is trapped in the fallen basin is the coarsest bedload component. So these are, it's a relatively straightforward, in terms of numbers that you want to understand, it's relatively straightforward, 1 millimeter a year, 10% trapped. And what has been intriguing, I think, is that there's been a lot of debate over the recent years about the extent to which erosion rates are changing through time. A recent study coming out from the Nancy team suggests that actually the sediment flux and erosion rate from the source area has been pretty stable through time in this case, from the Miocene times. There are obviously some fluctuations, and there could be significant fluctuations within this, but within the resolution of the data seems relatively stable. And similarly when you focus in on the Pleistocene. So the numbers are quite understandable, and the rates through time are relatively constant. So that gives us sort of context to where we're going. And what I wanted to focus on was four aspects. Whether I get to the last one or not will depend on how efficiently I talk. I want to start up in the mountain range, looking at the rates at which catchments are moving and divides are migrating, because that obviously determines the sediment dispersal to the mountain front. And it's something the techniques have enabled us to understand that much better in recent years. Then I want to talk about the grain size that arrives at the mountain front and the role of the gravel in controlling avulsion processes, rates of avulsion processes, and then an analysis of the way in which that transfers down into the sandy floodplains, and that the floodplain acting as a sort of buffer between the mountains and the coastline in terms of signals that can be transmitted down it, but then the potential for the extreme events that we've heard about from a few people that are able to perhaps connect directly from the mountain source system to the marine sink. So that's the sort of the topics I want to talk on, and hopefully I'll manage to get through them all in time. I think so. I'm going to start up in the mountains, and I'm just going to start with this observation that Niels Hovius made a few years ago, that on the long term and on the large scale, bedrock mountain catchments tend to have or converge towards a fairly uniform spacing along a mountain front. So if you look at somewhere like Taiwan, you can see here on the southern margins of Taiwan, we can see this fairly regular spacing of catchments and their outlets, with the outlets being spaced about a half of the distance between the outlets being about a half of the length of the catchments. So this length to width ratio, and here generated a lot of data, it converges around 2 to 3 or so. Although there are a lot of outliers out here, and as we'll see, the Himalayas is one of those systems which has a much more varied ratio and catchment shape. So let's have a look at that. If we start by thinking about the Himalayan system, in the simplest scenario, if the Himalayas behaved in a way that would follow many small mountain ranges such as Taiwan, we would see this is the drainage divide up into Tibet up here. This is the mountain front here. It's sort of just illustrated just up here as well. This is the sort of dispersal pattern we might expect, and you'd get a fairly regular. These arrows are just an approximation of what the area would look like and how the sediment dispersal would look like along the front of the mountain chain, delivering into the fallen basin. The reality is much more different. This is the reality over here. We have these highly variable drainage networks with highly variable shapes, many of which drain from around the back of the mountain system, behind the high peaks of the Himalaya, such as obviously the Tsangpo and the Indus system, but also the Sutlej here. But the ones we're going to focus on are the ones that basically form Nepal, the three here, the Karnali, the Gandak, and the Kosi, these big river systems, which have approximately a sort of equant shape. They're about the same. The length to width ratio is about the same. And of course, we're interested in how these might evolve through time and how this might impact sediment dispersal. So this is just showing some of these. These are these three catchments. They're colored as a function of their length to width ratio. And these are rather anomalously wide catchments. This, as we're going to talk about later down here, is Kathmandu. And so an interesting study by a good colleague, Sean Willett, looked at the way in which, and in fact these images are from Taiwan, looked at the way in which rivers in mountain ranges tend to compete with each other, the way the catchments compete with each other. He used this, the rivers' channels in these images are colored as a function of their erosive capacity through a metric that he calls the Chi metric. And as a result of this, you can see catchments, particularly on the right here. These are highly erosive catchments relative to this catchment in the middle here, which is being captured, and the drainage divides are shifting in towards that smaller catchment. As a result of that, that smaller catchment loses drainage area, the discharge in the rivers decreases, and hence the whole erosive capacity of that catchment reduces. The end result is that it's unable to counter rock uplift rates, and it gets uplifted and it becomes lower gradient as the erosion rates and the diffusion of the hill slopes lowers the net relief in those catchments. So a very interesting process that can happen fairly randomly, but can be driven by certain external forcing. And so this was a question to ask, is whether any processes like this might be responsible for some of the anomalies that we see in the Himalayas. And if that's the case, what sort of rates do they change at? And so what would we predict in terms of variations of sediment dispersal coming down into fallen basins? So this is elevated low gradient valley. And when we look at an image, a simple Google Earth image of the Ganga plains down here, the high Himalaya up here, Kathmandu stands out. The basin where standing at 1,300 meters high, it's this alluviated high elevation basin where the capital of the Himalaya is an obvious place for good agriculture, and it's now expanding very rapidly in terms of a city. So we chose to have a look at this and think about, well, why is this here? The obvious argument is that it's been blocked in some way by this structure, by the structures down here, but we need to understand the process a bit more if we're to think about rates. So this is a picture of Kathmandu looking, and this is the DM looking from the west. This is the Kathmandu Valley. You can see it's it's perched up here, very high. The surrounding valleys are much lower. Notice the asymmetry in the nature of the catchments this side versus that side. In other words, these much steeper catchments versus these alluviated lower gradient catchments. You immediately get the impression that these are likely to be moving, these drainage divides. The geology of the Kathmandu Basin is very interesting. It's perched up here on top of a thrust clipper of the main central thrust of a part of a remnant, the rocks of the high Himalaya. And it's confined by a mountain front to the south called the Mahabharat Range that are uplifting at about 1 to 2 millimeters per year. And the infill, the alluvial infill, comprises, starts at the base with these coarse conglomerates, the Bagmati Formation, that are about 2.5 million years old, 2.8 million years old. There is then a lacustrine succession, so the system was completely isolated and blocked off, and then we go back into the modern fluvial system. And here we can see these basal conglomerates, nice rounded, well abraded conglomerates overlying the underlying basement succession. And back in 1969, Hagen, who did a lot of the pioneering work around the Himalayas, he walked all over the Himalaya, he speculated that actually those conglomerates at the base of the Kathmandu Valley represented what was once a large transverse mountain Himalayan river system, and that subsequently, due to uplift of the Mahabharat Range, we formed a lake and the river was diverted off towards the east to join into the main Kosi River system. So there was obviously speculation here, and so what we've done is explored more carefully what the nature of this catchment is in terms of the processes and the geomorphology. And what I'm showing you here is a map of Nepal where the color tone represents, let me just see, I thought I had, there we are, represents the normalized gradient of the river channels, normalized for upstream area. So what it's showing is where the rivers are red, where the channels are red, it means they're much steeper for upstream area, and they're eroding faster into the underlying rock. So we can see here that boundary between the main central thrust coming along here, in the high Himalaya with high erosion rates here, relative to these bluer areas down here, and much more diffuse over here in the Kanali. And that as we zoom in, and we look at the Kathmandu catchment, we can see it here. We've got these blue rivers. That means relatively low gradient river channels for relative to upstream area in this alluviated catchment here. Then we get the steep river, the gorge, cutting down through this, what's called the Mahabharat Range, then joining down into one of these dunes or the Hatauda Basin before exiting into the plains. So this sort of perched system up here. And we're going to use a number of geomorphic metrics to evaluate the nature of those drainage divides, the extent to which they have an asymmetry of erosion across them. So we're zooming in on the, oh, there we go, sorry. So here we can see 3 images of the same area. These are all showing this is the Kathmandu Basin. And here we're showing the steepness, normalized channel steepness of the rivers. We can see the red surrounding the area with the blue in the middle, as we expected when we looked at those images. We're looking here at the local relief, these vivid colors, the pinks and blues are the local relief. That's basically the topographic relief between the valleys and the peaks. And we see these steep, high relief regions just on the margins of the drainage divide relative to the lower relief regions. It's not uniform all the way around, this signal. There are places where it's much more uniform across that. There's a reason for that. But the asymmetry is very clear in some locations. And similarly, if we go here to the mean slope, the mean hill slope, we see that asymmetry as well with these much lower gradient portions in the middle. So all those geomorphic signals tell us that the drainage divides will be moving in response to an asymmetry in the erosive nature of the landscape. So that Kathmandu Basin will be shrinking. And the other way of looking at it as well, and to understand it, is to look at the long river profile. So here we're seeing the long river profile of the Bagmati. This is the long of the Kathmandu Valley. And that's this blue one. And notice it has the flat region of the valley, and then we've got a nick point, steep region here with high relief. These shaded areas represent the topographic relief. Compared to the 2 valleys either side, this is part of the Kosi, this is part of the Gandak. They are nice graded profiles that go right down to the plains. In other words, their base levels are determined by the subsidence rate in the plains. The base level of the Kathmandu Valley is determined by the nick point and the rate at which that can slice down through the underlying hard rock. So it's basically a perched basin that is vulnerable to drainage capture as a result of their surrounding aggressor catchments, which are connected to their base level at down in the fallen basin. And you can see that if we just show you this, here we can see the Trisuli, this is part of the Gandak system, incising and eroding, and the arrows showing the drainage divide migration, and the south is to the right, the basin is down here. So we believe that this is a system where the drainage divides are moving and eating into the Kathmandu Valley. And the reason for this, we've been exploring using numerical models. This is work by Thomas Bernard, showing that if you start, there's some experiments just looking at the evolution of drainage divides. This is using a numerical model called Fastscape, that as you progress through time, if we just establish the erosion rate within normal catchments, where there's a slight tilt in the uplift history, which means there's higher erosion in the north than in the south. And then this dotted area is where a block of harder rock, which would reflect an uplifted thrust sheet perhaps, is suddenly exhumed to the surface. And what happens is that the erosion rate in the upstream area decays rapidly. So because you're blocking it by the uplift of a hard lithology, and this area upstream then becomes vulnerable to capture by the surrounding neighboring catchments either side. And so the tones here, we can see the reds here and oranges indicating high erosion rates associated with the divide migration. And as time progresses, this catchment eats around the margins of and in fact, in this case, completely removes the whole victim catchment, the remnants, the higher parts of that catchment. So you end up with the expansion, the lateral expansion of catchments, which are linked to their base level of, in this case, the fallen basin, as opposed to those catchments which have a perched base level linked to, in this case, the exhumation of harder rocks through a thrust sheet, or maybe just the exhumation of harder rocks. Okay, so that really confirms, that enables us to understand the sort of processes that were being looked at here in terms of drainage capture and the evolution of these networks, and therefore the rate at which the catchments that deliver sediment to the fallen basin will evolve through time. So if we think about just summarizing that, the drainage capture has led to expansion of aggressor catchments, such as in this case, the Gandak, and the COSI, and shrinkage and uplift of victims, in this case over a 2 to 3 million year period, leaving a short, small little river system with the remnants, if you remember, at the base of it, of the Kathmandu Valley, of what once was a much larger trans-Himalayan river system. And of course, this has implications for evolving provenance and to sediment flux into the fallen basins. So this is ongoing work, actually, that's only just, it's been submitted once and is in the process of being revised. So I'm now going to move on. We're now going to think about how sediment, all this sediment that's generated, once it arrives at the mountain front, what the nature of the fan systems are, how they vary along their strike, and the implications for processes of sediment dispersal, particularly avulsion. So here we're looking now at, this is work of Lizzie Dingle in her PhD, and you'll see a few illustrations of her work, some excellent studies in this region. Here we can see the main rivers draining the catchments of the High Himalaya. Again, you'll recognize the Kosi, the Gandak, and the Kanali. So this is Nepal here. We were just looking at this area of Kathmandu. And we're going to look at some of the characteristics of these river systems, particularly at the mountain front. And what Lizzie did was, first of all, evaluated the extent to which these rivers are incised into the plains or super elevated above the plains. And the way she did this was using a swath profile method on the DEM, on the SRTM DEM, where the colors denote the elevation of the topography relative to the channel through either the nearest point in the river channel. So here we can see an example where the river channel runs through here. These areas are much lower in red. So anything that's yellow is about the same elevation as the channel. Anything that's red is lower. Anything that's blue is higher. So you can see the mountain front here. So you get this idea of a perched channel or an incised channel. And so she did this for the whole mountain front. In this rather dramatic looking image, we can see, so Delhi's here, this is the Yamuna. We can see here that these rivers in the west are clearly incised into the plains. They have a broad alluvial valley, maybe tens of kilometers wide, but it is lower than the surrounding plains. In contrast, as you go to the Gandak, it's almost at the same level. And as you go to the Kosi in the east, it's super elevated. Its elevation is higher than the surrounding plains. And we'll be looking at that in more detail later. And of course, this has implications for the morphology and sediment dispersal of these systems. The other aspect of each of these rivers is the position of this very important transition, which I'm going to be talking about quite a lot in this talk, is the transition between gravel and sand. This has been widely recognized from rivers all over the world. There's been some excellent work by people like Mike Lamb, Jeremy Venditti, and others, identifying gravel-sand transitions. And we can see here that as we go from west to east, so from the Yamuna, Delhi way over to the Kosi, we can see the gravel-sand transition moves, this is distance from the mountain front, moves closer to the mountain front. And that these transitions are associated with a break in the long profile of the river systems. So upstream, the gravel systems are steeper, downstream, they're lower gradient, as you may expect. So note that change as we go east. And the other quite big question, obviously, for all of these systems is there a significant change in the sediment supply? So I'll bring all this information together, but is there a significant difference in the sediment supply from the mountain catchments? Now, when we're trying to evaluate sediment supply from mountain catchments, it is a tricky game. Whether you're trying to look at suspended sediment loads and projecting those, or whether you're trying to, in this case, use detrital cosmogenic beryllium-10 from the sand, which is this work by Martin Lupka. And this is really the first way, and the best way I think we've got, the best insight we've got so far into whether there is any extensive difference in the recent erosion rates from these catchments. So in blue are the equivalent sediment flux data, in red are the erosion rate data. They do vary highly from each catchment. The stochastic nature of mountain catchments means that it is always tricky to get a reliable long-term signal. But there's no, I would argue that there's no major change as we go from the Ganga. The Kanali is variable. To go from the Ganga over to the Kosi, the erosion rates are fairly comparable. And as you may expect, having traveled through then going through the plains, the erosion rates appear much more constant. The system is mixed and well buffered by the time you get to the delta. So no huge variation in sediment supply as far as we can tell. One other interesting observation is that the gravel flux to each of these catchments is comparable based on calculations of gravel volumes and the distance to the gravel sand transition, which is mapped along the mountain front here. And this is just showing the geology upstream. And note as well just how close and proximal that gravel sand transition is to the mountain front. But when you look at the volumes of gravel within these systems, so this is converted to gravel flux, they're fairly similar along strike. What you'll see is these very small little catchments. This is from some of the catchments studied by Dubil and Lave. I haven't put their reference in, but an excellent paper. These smaller catchments here, we see that when you normalize the total gravel volume for upstream area, these actually have quite high gravel fluxes. But overall, the gravel flux is not that different, regardless of catchment area. And the argument that Lizzie, that we made was that this was because the bulk of sediment generated in the upstream parts of these catchments is converted into sand through abrasion. If you look at the sort of calculations of abrasion rates and flume tank experiments by people like Michael et al., my colleague in Edinburgh, you can argue very carefully, as we did in this paper, that abrasion rates will dominate and remove the bulk of the signal of bed load from the upper parts of these reaches, upper parts of these catchments. So we have this relatively small amount of gravel deposited along the mountain front. The other interesting thing about the gravel is, of course, its fining rate, and this has become an interesting theme that a number of colleagues have focused on. And Philip Allen, my old supervisor, is particularly interested in this topic. And so looking at the fining rates as you go down to the gravel sand transition also relates to the total sediment flux and substance history, as we'll come on to. And when you look at these river systems from the Yamuna, then getting progressively further east to the Kosi, what you see, these are the D50 values in black, and the D84s are the empty symbols through here. The gradients, the rate of change as expressed by this exponent alpha, is at the highest in the Kosi catchment. So the Kosi catchment, notices the horizontal distance is much shorter here, so that's this is much steeper. The Kosi catchment, the rate of fining is the highest as well. So we have a number of factors here, which we've looked at sediment flux, we've looked at fining rates and grain size, and one of the other key parameters that we really haven't looked at yet is the nature of the substance along strike. There's nothing in these components, which the grain sizes are, the mean grain sizes, the D50s at least, are very similar, which I should have highlighted on the previous slide. The sediment fluxes, we believe, are fairly similar. So is there any evidence that there's any change in subsidence along strike? Well, this analysis of the depth to basement along the mountain front suggests that the deepest part of the basement are towards the east in these regions of the Gandak and the Kosi. The basement depths beneath the fallen basin are shallower and more towards the east. And if you look at the depth of the flexural basement, the basement of the fallen basin, and you combine that with the convergence velocity of that plate beneath the surrounding mountain belt, you can get a proxy for subsidence rates. And so this is what we were looking at and modeling in this paper here. And so we argue here that subsidence is playing a key role, that the rate of subsidence as you go further along strike towards the east, the increased subsidence rate is causing a much more proximal gravel sand transition. It's a higher fining rate. And as we'll see, the behavior is also quite different in terms of avulsion histories. So summarizing there, a west to east increase in, there we are. West to east increase in substance rate, increased rates of downstream fining, more proximal gravel sand transition, GST, and fans perched above the floodplain as you go further east. And this, of course, has implications for the degree of sediment trapping, with if it's 10% average sediment trapping across the fallen basin as a whole, but is that dominantly towards the east? So in other words, is the signal that comes out to the delta much more influenced by bypass of the rivers in the west, the Ganga, the Kanali, and the Yamuna, for example? So that's sort of an overview of some of the nature of the gravel fans, but let's think about their behavior as well, their longer term behavior in terms of avulsion. So we're going to look at these three examples. If I start with this lovely study by Chakraborty and others on the Kosi, at least lovely image, which the Kosi fan is renowned for its flooding in 2008. The Kosi, the discharge point here of the Kosi River, broke through the embankment. Of course, this is all huge embankments funded largely by the World Bank around this region. And we can see the stippled red represents the area covered by when the avulsion took place in 2008, displaced about 3 million people. Notice, so these are all positions of the river channel based on historical maps that Chakraborty synthesized. We can see over the last few hundred years how that channel has migrated to its present course, which is this wrapping right around the edge of the alluvial fan. So a highly mobile and avulsive fan system of the Kosi. And if we look at cross sections of the topography, we can understand why. And as we said before, this is a super elevated channel system over a large elevated alluvial fan. The elevations are not huge. I mean, let's just check here. You know, these are only for 10 meters or so, the variations, but it's enough to highlight and enhance the mobility of these river systems. If we then go much further west, to a very nice study by Singh et al. They looked at the nature of the Paleo-Sutlej river system. The Sutlej now, which is over here, drains into the Indus fan, but they argue this from this study that about 8,000 years ago, the Sutlej actually flowed into the Ganga. So there was an avulsion node up here above the gravel sand transition, just as it outlets from the mountain front. And it once flowed in the former route heading east towards the Ganga system. So that's, again, we've been talking about the way in which these, over a few million years, these rivers expand and contract associated with drainage reorganization. In this case, you get these abrupt flips and what would be a significant increase in discharge and sediment supply to the system through avulsion of the channels at the head of these gravel fan systems. And then we've been also looking at this for the Kanali, and this is interesting. So we've been trying to understand this. Here's the Kanali, which is the central, this river system here. This is the gravel fan. There's the gravel sand transition. This is an image of up here of the river as it exits near the mountain front. Notice this high terrace around here. And then as it goes out onto the plains out in this region, we have the main terraces picked out by the jungle here. This is the Bardia National Park. And in here, we have in the modern river plains of the river, we have lots of abandoned paleo channels. And this is for Laura Quick's PhD, we did OSL analysis of the terraces. We measured OSL in the terraces and in these paleo channels, and we got ages for the terraces of up to 7,000 years, and for the paleo channels, they're right next to the modern river system, of between 500 and 1,000 years. It's a much older one over here. So these are indicative of a much more stable gravel fan system than the Kosi. So there's very interesting questions as to why there is this degree of variability in the avulsion, the characteristics of avulsion. This is actually not, it's not confined by terraces in this zone. There's no reason why this shouldn't move around as much as the COSI within the terrace system, but it seems to be relatively stable in its channels compared to the COSI. We do have suspicions as to why that might be, but that's a part of an ongoing study. So let's just check where I am with my time. Good. So then we come down. That's sort of overviewed some aspects of the dynamics of the upstream mountain drainage networks and of the nature of the gravelly fans and the way the controls on their morphology, potentially linked to subsidence, and the nature of and rates of avulsion of these channel systems. If we come now down to the gravel-sand transition, this is a key boundary into the next sort of geomorphic domain, and we wanted to understand more about that boundary. So we're sticking to the Canali system. It's one of the least anthropogenically modified river systems along in the Himalaya, and we were posing a question that if we believe I'm sorry, let me just backtrack. If we look at the long profile of the Canali River, here we can see the long profile here. The gravel sand transition is marked by this gray band. We can see the slope values decreasing as we go through that. When we went out there, we thought that, well, because of the reduced gradient, we might expect to see rapid sediment dumping out of the channel, the water column, at the gravel sand transition, and hence an increased bed aggradation and increased rates of avulsion and switching and a different behavior of the system as we go from the gravel down into the sand. And so the way we thought we would test that is to look at the concentrations of suspended sediment for one time interval during the monsoon from where the river exits the mountain front, then progressively downstream to just beyond the gravel sand transition. Sorry, I didn't mean to say this is the gravel sand, that's the Indian-Nepal border. The gravel sand transition is in this yellow band. So we've got one measurement site below the gravel sand transition and 4 above it. And so that was the approach. So the way we were going to do this is by borrowing a boat from our good colleague, Ed Tipper, who gave a very nice talk in this session previously. This is his boat, which enables you to go out and sample. Combining that with an ADCP, this is not a great ADCP example, with that's not been infilled at the base, but combine this with an ADCP, it means we can evaluate sediment concentrations, and with the ADCP convert that to total sediment fluxes. So we went out during monsoon discharge, and this is the sort of nature of what you're doing. I think Ed showed some of these examples. You're trying to locate and do with your Van Dorn's sediment sampler, you're trying to drop that at the same location each time to variable depths. So here we can see Lizzie, who is fantastic at working all this equipment, me just trying to pump the Van Dorn to lock it shut. We then drag it up. Here's Lizzie pulling it up, and we've got our sediment sample. And we did that at each location. As you can see, the river's flowing quite rapidly. This is sped up, actually, of course. But we did this repeatedly at these 5 locations for different depths. And the results look like this. So there's T1 to T5, and T5 is generally the yellow dashed line in these top data, and so this is just plotted to normalized channel depth. The actual depths are about 8 to 11 meters, and what we're seeing here is grain size above the gravel sand transition. We see grain sizes that are fairly uniform as a function of depth. And as we go to the second plot down here, we see sediment concentrations that are remarkably uniform. So they're really effectively wash load. They're fully suspended within the water column. Once we go down across the gravel sand transition, we see grain sizes dramatically increase towards the lower part of the water column, and we get this nice increase in sediment concentrations towards the riverbed, and very high concentrations, much higher than upstream of the gravel sand transition. So this is not what I think we expected when we went out there, such high sediment concentrations and increases in grain sizes. And when you convert this to total sediment flux through the channel at this time, it implied a significant increase in sediment flux across the gravel sand transition. So actually the opposite of what we were expecting. When we were there, this is actually during the winter, during the non-monsoon period. During the monsoon, this is the margin of the river just downstream of the gravel sand transition. We can see the riverbank. As I was standing here during the monsoon, this riverbank was collapsing at a rate of about 1 meter every few minutes. There would be large slumps as the river was fluxing through. And Lizzie then looked at the Landsat data immediately south of the gravel sand transition, and you can see that that's happening as these channels are migrating rapidly across the floodplain, reworking the floodplain during the monsoon discharge, so recycling material into the channel and depositing material. And so we believe that this process of recycling and erosion of the banks is the key process, that is the key reason for such an increase in sediment flux and recycling of coarser material as well into the channel system. So to summarize, the gravel sand transition, the gravel sand transition forms this boundary between these relatively fixed channels which avulse every few thousands of years or hundreds of years, relative to and they pin this key point here, which then acts as a pinpoint downstream of which the rivers are rapidly migrating, and where the sediment is exchanging with the riverbed through and the margins of the river to get these very high suspended sediment loads. What of course this means is that this is acting as a significant buffer between the catchment and anything downstream of this point. Any sediment that comes out of this system has to have been recycled from within the floodplain. And so the conclusion of that part, and this is very near the end now, is that the floodplain acts as a significant buffer through storage and recycling. And in fact, a presentation by Martin, who's been using cosmogenic carbon-14, reckoned that the floodplain stored sediment for about 20,000 years. It was somewhere between 10 and 20,000 years from the mountain front to the delta. So very interesting results there. And the last question is, okay, so that's the sort of stable structure of the system. Can extreme events punch through this buffer? Can we occasionally connect directly from the mountain front down to the marine system? And obviously some of you working in this area will have witnessed or been aware of some of the interesting data, for example, that's come out of the Bengal fan, this wonderful studies by Christian Fraslano and colleagues. And this core site from IODP in the Bengal fan, U1454, they've recorded these remarkable presence of sandy beds rich in woody debris. Much of the woody debris working with botanical experts, have identified this material as coming from sort of medium to high Himalaya, 3,000 or so meters high, particularly conifer trees. And the woody debris has survived in sandy components, sometimes forming up to 80% of a bed, which must record extreme discharge straight from the mountain front coming down across the plains into the Bengal fan, or at least this is something that Christian is working on at the moment. And then of course, earlier on in this season, these series of talks, we heard from Steve Goodbread, a wonderful presentation and some very interesting analyses here from the upstream of the Bengal fan, which is extraordinary. published by Pickering et al., showing these gravels, 30 to 90,000-year-old, well, more than gravels, cobble beds down towards the delta front, recording these huge, filling in these huge paleo valleys, which are up to 40 kilometers wide, which must represent some sort of what you might term a mega flood, but huge extreme discharge. In this case, they were speculating that it might be linked to the sort of lakes in Tibet that Dave Montgomery has been working on. So clearly, big events can bypass the buffer of the floodplain. And we thought an opportunity following the Gorka earthquake. We wondered to what extent an extreme earthquake, or an extreme earthquake, but a major earthquake might impact the sediment flux down into the plains in the sort of way we've been thinking. So a student, Emma Graff, has been working on this. This is the distribution of landslides mapped by Roback et al. Following the Gorka earthquake. This is Kathmandu here. Here's the tributaries of the Kosi River, which flow right through some of the major landslide material. We can see that up on the left-hand side. And as you go down to the mountain front, we see this sandy plain, these sandy rivers. The question we had was, following Gorka, how much of this coarse bedload material could be transferred to the mountain front and could then influence, say, for example, flood vulnerability towards the mountain front due to reduced capacity of the river channels. Actually, what was very interesting was that, so here's her work up in the Malamchi Kola. This is a small tributary, beautiful valley here. We can see this alluviated valley. When she's been documenting using the satellite images, the distribution of gravel and vegetation within these channels following the 2015, so this is that's the 2015 earthquake was in here. The gravel has been approximately stable. There's not been a huge signal of sediment flux from the high mountains down to in the lower reaches of the catchment. So there has been some record by colleagues at Potsdam who have shown a record of suspended load, but the bed load does not seem to have been impacted significantly. And this is probably linked to the connectivity between landsliding and river channels, and that what is waiting for is basically the next big monsoon. So very monsoon dependent sediment flux, as we talked about earlier. And lastly, we've also been looking at the Siwalik sediments to see whether there's evidence in the Siwalik successions of some extreme events. And so when we take a section of the Siwaliks here in towards Dehradun in this area, in India, we have the middle Siwaliks recording the sandy plains. We have the abrupt transition into the upper Siwaliks. That represents the paleo gravel sand transition in the Siwalik succession. But below that gravel sand transition, we do see evidence of these intermittent matrix-rich conglomerates, up to 2-3 meter thick conglomerates that are breaking through into the middle Siwaliks with these thick components. And based on reconstructed distance from the gravel sand transition, and then with sediment entrainment calculations with our colleague Maggie Creed, and when we compare it to modern rivers, it indicates a discharge of about 23 to 28,000 cubic meters per second. And we believe that these outrunners are enhanced by the transport of bed load in these outrunner flows is enhanced by the high sediment concentrations near the boundary layer. Okay, some conclusions, my last slide. So we looked at the expansion and contraction of Himalayan mountain catchments, which we believe occurs on the scale of a few million years, must have implications for sediment yield into the fallen basin. We have gravel fans that are 10 to 40 kilometers long with similar volumes, regardless of catchment size, and where we think substance influences a large component of their morphology, the avulsion frequency, which also varies along strike. And then we came down to the gravel sand transitions, which records this downstream change from intermittent avulsion in the gravelly fans to rapid channel migration, buffering the signals from the mountain range down to the plains. And lastly, we wondered to what extent there are extreme events that can pulse and beat through that buffer. And indeed, there are examples of that. But to understand the processes, I think we're really not there yet. Good. Well, look, thank you very much for that. And I'll now stop sharing and hand back to Paul.
Great. This is I'm sorry, it's a little bit echo sound.
I'll turn off my mic.
Okay. So this is a great talk. Thank you very much. And so such a great field survey, and understand how dynamic of the channel. So let's see if anybody have a question, and you can go ahead, unmute yourself, and go ahead to ask.
Sure. Hi, Hugh.
Hi, Mike.
Hi. Yeah, no, really interesting talk. One thing I find interesting is that the western rivers, like the Yamuna and the Ganga, are incised, while the Kosi is perched. But by the Kosi, you say, is where the subsidence rate is greater. So can you explain that difference of why the faster subsidence rate has a higher river versus the incised river?
Yeah, I mean, I think the way we understand that is that any of these river systems, as recorded in the terraces anywhere around the dunes, the piggyback basins, or at the mountain front, there are clearly fluctuations in sediment yield and hydrology, which do cause natural variations in the base level. And areas where you have relatively slow subsidence, the likelihood of that recording, particularly base level drops linked to changes in water discharge or sediment yield, is higher than areas where you've just got rapid subsidence. As long as you're subsiding very rapidly, then there's no opportunity for basically the sediment yield will always be trying to keep up with the subsidence rate. So our understanding there is that basically the sediment supply is constantly trying to fill in the void generated by the rapid subsidence, and there's no opportunity for base level fluctuations to be recorded. It just keeps piling up, making it more vulnerable to perched and more vulnerable to avulsion.
Yeah, it has the higher avulsion rate.
Yeah, that's the.
Okay, Hugh. There's a couple talk about Amazon. Amazon, they from Andes Mountain, they believe 85%, 95% is from the mountain, coming down. How about here, in the Ganges system? How much the sediment we get estimate is from that operate the mountain coming down?
So you're asking from the uppermost mountains or from the, do you meaning what proportion of the sediment comes from the high Himalaya versus the foothills?
Yes, something, or even from the whole mountain, compare the middle or low ridge.
Yeah, the distribution obviously varies in terms of the highest. When you look at the thermochronology, you can demonstrate that the greater Himalaya, bound by the MCT, the main central thrust, and the South Tibetan detachment, is exhuming at very much higher rates than other portions. So as you saw on the channel steepness, that's where the bulk of the sediment is coming from. And in fact, if you superimpose on that, there's this very nice coupling. I just don't have time, but there's a very nice coupling with the precipitation. The orographic signal of precipitation is very localized at the mountain front, and then there's a band up at the high Himalaya. Okay. And that coupling of high exhumation rates with high precipitation rates does localize the exhumation. 1 millimeter a year is an average, whereas it is very localized, or is reasonably localized.
Okay, so in one slide you mentioned, the wash load gradually decrease, but bed load increase. So what's the percentage we talk about? How much of the bed load, in the river you studied?
Basically all of the, during the monsoon, it was all wash load during up above the gravel sand transition. And then when you got down below the gravel sand transition, you got this typical sort of Rouse profile with very high sediment concentrations near the bed. I can't remember the exact numbers, I'm afraid.
Yeah, because this is always challenging the community figure out how much suspended load was the bed load. Of course, each river is different, every river. But
absolutely,
that's interesting. Anybody from the audience, if you have any question, go ahead, unmute yourself and ask, or you can type your question. Anybody? So here, did you see any influence of that global warming with the melting of the glacial, the more ice sheet melt down? Did you see any signal show that kind of increase or water discharge or sediment discharge?
I mean, I think the work of Lupka and others on looking at that, or not much. That's that recent paper showing that the relative stability of erosion rates at the delta front through these variations in climate is provocative. I don't know. It obviously needs investigating, but it suggests that actually the system's pretty robust, and it may be that, in other words, that the numbers are pretty constant despite their expansions and contractions of glacial extent upstream. But what we did, we didn't look at that in detail, I'm afraid.
Okay. Yeah, interesting. Yeah, some data I have show looks like the water, discharge steadily increasing last 20 years, but I need to verify, but sediment, I don't know, because
I mean, I think one of the worries is that there's so much anthropogenic. I mean, there's so much damming, so much irrigation that I mean, there's been a number of papers worrying about the impact of the delta. Although if the delta is so buffered from what's going on up in the upstream reaches, then perhaps there's a few thousand years at least that the delta can happily continue being supplied by recycled floodplain before we need to start worrying. But maybe that's a little controversial, I don't know.
Okay, anybody from the audience? If anybody have a question, comments? Michael, you unmute, you mute yourself.
Yeah, Hugh.
Yeah.
One of the really interesting figures you had was showing, the sediment flux out of the different river systems, where it's just really noticeable that the two syntaxes are dominating the system and have captured a lot of the sediment. Do you have any good reason as to why that's going in? They've both come around and captured the entire backside of the system. Well,
I think with those ones, I suspect they haven't captured. I think they are inherited from along the Indus and Sangpo rivers. You have remnants of intramontane basins all the way along there, and with fluvial deposits. And I think they are inherited from the sort of at the boundary between the Asia and the Indian system. That there's always been a sort of a valley that's run along there. I think it's inherited rather than captured.
Sort of essentially this suture delta.
Yeah.
And do you think that's typical of other mountain systems, that there'll be something like that where I think there are signals of that in the Andes, I think, although I'm not an Andes aficionado, but I think there are components of that. Yeah. The other part of that story, of course, is that you're in the rain shadow there, so the ability to capture, I mean, the ability for the transverse rivers to perhaps capture up into the Indus and Sangpo is limited because they are in the rain shadow, so their erosion capacity is much less.
Wonderful. Okay, anybody else? If no, Hugh, I think thank you very, very much for this great talk. And I think our colleague, if you like, you can turn on your camera and you can say hi. And so please remember this coming Friday, Carl Wilson also give a talk about the Ganges, mainly the lower part. So that's a great. He'll talk about the upper part, Carl Friday talk about lower part, elevation, sediment discharge. I think we will get much better understanding again the Ganges. So that's great. And maybe think about, we can maybe, Michael, maybe think about put some special issues or whatever, put together. Yeah. Okay.
Nothing better to do, Michael, have you?
Yeah, that's what I need is
That's great. That's great. Okay. If no, we can end it here. Thank you very much.
Okay.
Yeah. Great.
Thanks a lot, Paul.
Sure. Thank you, Hugh. Oh, this talk will also available on the YouTube. In 24 hours.